If you're interested in the real performance of the Foreign Linker API, you're right in this video. Hey guys, how's it going? Today we dig a bit deeper into the performance of the Foreign Linker API. Recently I was asked if I could provide some numbers how fast the Foreign Linker API is, and particularly you're certainly interested in comparing it with, for example, JNA or JNI. So here we go. Certainly I have provided a bit of code for you on GitLab, so you can just pull it down, check the readme.md file, and you're fine to repeat all the steps I'm showing you here. I'm using the Java micro benchmarking harness, which makes repeatable benchmarks really easy. It does its very best to warm up the Java virtual machine and to provide really repeatable numbers. It's a great tool. Look it up on the web, Java micro benchmarking harness. Using it is really easy. What you need is just a main method where you enter with your primary thread. Then you start the Java micro benchmarking harness, and what it does is that it looks up all the methods having an annotation of @benchmark, which means this is my benchmark. So I have 4 benchmarks here and they will run in sequence. So the first benchmark is I will drive the original Java implementation of getting the length of a string. So what it does simply is, here's the string, which is hello, and it's passed into this method. And my method in the JRE implementation is simply that it checks for null, and when it's not null, it's giving its length. So this is our baseline we want to measure, so we know how fast is our computer at all. The next one we want to measure is how fast is the de facto standard for native invocations, which is JNA, the Java Native Access, which is a third-party project, but is really well known and used by lots of applications currently. And it's rather easy to use. You can look it up on the web, JNA. There's a great website explaining it. And we do the following code with JNI. So we load the kernel 32 DLL from Windows, which provides a function we want to actually invoke for getting the length of a string. And here you see the invocation is rather easy. In the DLL instance, we want to invoke the lstrlen function. The next one we want to measure is the fastest way how to get into native code from Java by an official way. So we look at the JNI, the Java native interface. And what it does is you declare a method in Java, but it is annotated as being native. So there is no implementation at all. Looks like an interface somehow. And the implementation is provided in a special DLL or shared library, and you have to write that DLL or shared library according to the rules laid out in the JNI specification. So we have to provide that, and you find it here. Wow, that looks scary. This is a lot of boilerplate you need just to make it a good citizen on Windows, more or less. On Linux this looks a bit different certainly, so here you have a big difference. On Linux you have to do other things than you do on Windows or on Mac. And here you find the special way JNI wants you to call the methods in your native code, and the code you have to call to convert the strings the way Windows wants to have them, which is UTF-16 LE. So it's not that trivial. Certainly you can do copy paste or something, but it's good if you know the C++ language, and if you don't, you need a colleague or coworker, or you have a problem. Now finally we want to measure how the foreign linker API compares, which still is an incubation, so it's a bit unfair actually, because it's not done, it's more like a proof of concept, you could say. So I assume it will be fast in future, but let's measure it in comparison. You know this boilerplate from my last video, which you can see here. And here you see what happens inside of the my method invocation. It does the same UTF-16 LE conversion, just like JNI does, but JNI does it inside of the C++ part. And here we do it inside of the Java part. So this makes a difference actually. And here we just give it the final text and do the invocation. So this looks much nicer than the scaring C++ part. And I'm curious whether it actually will be as fast as JNA or as fast as JNI, or maybe it's much slower. I'm really curious to see that. So let's get the thing running. I have provided a structure of POM files, so it's rather easy to compile everything when you have downloaded it. So just do a clean build and you see it will do everything you need. It compiles the Java code and it compiles the C++ code and links to a native Windows DLL. So sorry guys, this code actually is only for Windows. It won't run on Linux or on Mac. Maybe it's a challenge for you. Send me a pull request where you have added the code for Macintosh or for Linux or for other operating systems. Send it, I will merge it into the code base. And the compiler is done in 13 seconds. And what we need next is to invoke the actual benchmark. And it's not that trivial, but I have provided a README, and the README has the code line we need to execute. So we should be fine just by executing this one. So what we need to take care of actually is that we do the add modules for the JDK incubator foreign module, incubator foreign. Okay, I cannot type today. Because this module will not be on the module path otherwise, as it still is incubation. And we have to provide another flag, which is that some restrictions were removed. Otherwise we cannot native code. This is a security means built into the foreign linker API. And then we have to provide the Java library path, because we have written a new DLL, and that DLL must be found obviously, and it will be searched on the library path, and the library path must include it. So we have that. And next one, we want to start our benchmark driver, and this is inside of target driver. So here we are. Let's go. Now actually running this benchmark will need a lot of time. You will sit here for, let's say, half an hour, because for each of these benchmarks it will do a warm-up and it will do several passes and it will repeat the passes 5 times. So to gain the maximum precision in the benchmark result, the harness does the best it can, and this needs a lot of time. So don't sit here for half an hour. I have recorded it, but I will speed it up so you will see how long it runs in the end. But in the video it will be much faster. And I will go and have a drink meanwhile. Back again. Cheers. And yes, it's done finally. Great. So here we can see the results. Looking at those numbers, you will see this huge amount of invocations per second, which is thousands, millions, so 49 millions operations per second, or nearly 50 million operations per second in pure Java. What do we learn from that? Comparing it with any native invocation, Java is really fast. Whenever you think you have to speed up things, don't have the idea that going into a native DLL will be the ultimate solution. This is not the case. Switching from Java into your native code needs a huge lot of time. So keep in mind that short Java code will always be faster than going into a C++ DLL. C++ DLLs can only be used when you have to replace huge amount of Java code, which is really slow. Or when you need a function that you cannot do in pure Java, like for example accessing this webcam. You need to go to the operating system, you need to go to the driver to obtain this video stream, so you need to go into native code. This is the first thing to learn from these numbers. Now looking at the native invocations, we will see a clear difference between the three ways we can go. If we go through the Java native interface, the official way currently how to invoke native code, you will see that we have, let's see, thousands, millions, 6.7 million invocations per second, which is clearly slower than the pure Java solution, but which is faster and much faster compared to the new foreign linker API and the Java native access third-party DLL. You see here we have in the foreign linker API 2.76 million operations per second, and in the Java native access, the de facto standard currently in lots of applications used is only 0.44 million operations per second. So this means the Java native interface is really complex to do because you have to learn C++ and you have to build a DLL. But it is nearly or more than double the speed of the foreign linker API, and it's way faster than the Java native access. But this isn't the whole truth. The truth is that every benchmark somehow is weird and doesn't reproduce the actual numbers you would have when using these technologies in your application. I went to the OpenJDK team with these numbers and asked for some help. And the answers they provided were really interesting, and I did some more tests with their ideas. And the truth is, JNI really is that slow. Maybe I can tune that. I didn't ask the JNI team for help actually. But this is not about JNI. This is about the foreign linker API. So the foreign linker API has the problem. It's still an incubator. And they are trying out things and changing things. and the performance will be better in future automatically, on one hand. On the other hand, the way I was using the foreign linker API was not really the optimal way I could go. They explained to me that I could do better in 2 ways. The first thing is, let me show the code. It's easier to understand when you see the actual code. When I come into this method, I'm doing a conversion from the Java text into the C++ text. So that there needs to be some native memory containing UTF-16 LE characters, and this is performed in a way that is not optimal, let's say it this way. So what they do here is they grab some huge memory, and inside of that memory they do the conversion, and I get back a linker to that, and before they can write the original bytes into it, they have to zero it out, and after they copy the byte into it, they have to put a null byte at the end, because C++ expects that. So there's a lot of stuff going on. And now comes the interesting thing. After I have used this string, my try with resources block is ending. So actually, this memory is freed. So it's not only zeroed or something. It's really given back to the operating system. So it's gone. And when I come here for the next time, I have to find some memory somewhere in the RAM. So and the huge memory block is obtained and is zeroed out, and the conversion is done, and so on and so on. And the problem is that in reality, nobody will do that, because in reality you would have more C++ functions you like to call. So you can reuse that big memory for several function calls, and you can even reuse that memory for several invocations of my method. So if we could just register the original memory somewhere, like in a static variable, and then just reusing it, then it would be far better than doing it this way. It's just about throwing and zeroing out and throwing it away and reorganizing everything. So they asked me to change the benchmark a bit and send them the new numbers, which I did, and the result is really promising, and I will show you the difference here. In this version of my benchmark, I simply commented out the conversion of the string and leave the invocation as it is. I'm passing just null to indicate to the called library that I don't have a string at all. So the invocation still happens, the operating system still does something and give back a result of 0, but we just move aside all that internal automatic string conversion and memory allocation and zeroing out and reallocating memory and all that. So let's see what the numbers change when we do that. And you can see here the benchmark is still running, but the numbers are okay, that we gain about 6 million operations per second now. So we come very near to JNI, but with the benefit of the simplicity of the Java native access library. So we have the best of 2 worlds here, simplicity and high performance. So now you would say nobody needs that because you have to convert the string. Sure, but there's a trick still. And here you can see this trick. In fact, it's just one of several tricks they told me, but this trick alone is rather impressive still. What I actually do is that I pass a third parameter to the conversion method of the string, which points to a pre-allocated memory region in the off-heap memory. The off-heap memory is like the real memory of the operating system. So what this does is that it simply uses this pre-allocated memory and just puts in the converted characters into it with every invocation of my method. So it doesn't reallocate again and again and freeing again and again, but just allocates once, here, and then reusing that memory. And when we do this, the numbers are rather impressive. I have reduced a bit the number of iterations and warm-ups, so sorry, the numbers are not that accurate now, but we can see them live. So we get a whopping 6 million operations per second in foreign linker API. 6 million operations per second with converted strings, and the code still is rather easy. We just added one line and pass a new parameter. This is great. I actually think this trick alone is good enough for most applications, and they will do more tricks. By the way, don't use that code literally. I have not freed the memory region that I'm using inside of the scope. Because there's a problem on Windows 10. Again, it's still an incubator, okay? It has bugs. And it tells me I cannot free the memory. So, sorry for that. I'm actually creating a memory leak here, but this is just the incubation code on Windows 10. It will run in the final version, certainly with freeing the memory. So, where were we? Yeah, right. There are more tricks. Let's see another trick. And for this trick, we have to look into the actual source code of the CLinker class inside of the Java runtime. So here we are on GitHub and open JDK, and we can see what happens inside of the conversion of to C string. So how is that code working that converts the Java string to the operation system strings? You can see here I pass in my native scope, which is fine, and which provided us 6 million operations per second already. And you see here, inside of the scope, there is an allocate operation. And this allocate operation actually will provide a piece of information inside of that pre-allocated memory and zeroes out that one and then copies the bytes into it. And after that, I, in my code, throw away that allocation. So the next time we come in here, we still have the scope, but we do the allocation again. And this is rather nuts because we know we need this memory a lot of times. So what we could do is actually to copy this code from here into our own application and use a pre-allocated memory segment to just copy the bytes into it, which means we don't call to C-string in its original form. I actually tried it out, but unfortunately I have thrown away the code. But believe me, it's another benefit from 6 million operations to 6.5 million operations per second. 6.5 million. That is really near to JNI. And then I went with these numbers to Maurizio, which is the lead of this foreign linker API specification, and I had a really great discussion with him. Thank you, Maurizio, by the way, for taking the time and looking into my numbers and looking at my code and providing all the great examples that you provided last week. And Maurizio came up with an idea that he might provide in the final version of the foreign linker API. And this trick he might provide will be even faster than JNI. Yes, the foreign linker API will definitely outperform JNI. So what is that magic trick that Maurizio described to me? We have seen that currently we are reusing the scope in my application, which is nice and which brings performance. But inside of that scope, the toC string method still allocates memory, and this needs time. So what Maurizio is planning is we have a pluggable allocator, and that allocator might be reusing memory. What does that mean? That means we just allocate once, then in any invocation we do, the string conversion will not reallocate memory, but just overwrite the old memory. That means we spare completely the reallocation of memory and the freeing of memory. And this is the slow part that is left over here. In the end, we have measured out what the result would be, and the result would be that we can, in some circumstances, outperform JNI, because JNI has not such a reallocation algorithm. JNI will always do a malloc call in the operating system. So Java here really rocks, because in future, in the final version of the foreign linker API, please Maurizio, add the reallocation algorithm. We will have a faster native access than we have currently with JNI. So to sum up the results of today, the foreign linker API is in a very early incubation state. Sure, it has lots of bugs and it's not performance optimized yet, but it already outperforms by far the current de-facto standard JNI Java native access. And with a few tricks, you can be even close at the performance of JNI. You have seen that we reached 6 to 6.5 million operations per second without huge tricks, just with one more code line. And if Maurizio adds the reallocation algorithm, and I hope so deeply that he really does, then we will even be superior in the performance than the Java native interface. So this means in future we write code as simple as with JNA, but with the speed or even better speed of JNI. And this is a game changer in calling native code. If you like this video, I would be really happy if you give it a thumbs up. Please subscribe to my channel to never miss a new episode. And for the time being, stay healthy and always party on. I want to say thank you Maurizio and your team for helping me in the preparation of this video with your kind advice and discussions and judging my numbers and sending me code samples. This was really great from you, and this video wouldn't exist with your kind help. Thanks a lot.